Hello everybody, Professor Parth here, and today we're going to be discussing half-life. Half-life is a concept of physics in the portion radioactivity. And radioactivity is essentially a study of radioactive items. It doesn't matter what they are, but that's radioactivity. And half-life in radioactivity is essentially the interval of time required for half of the atomic nucleus of a radioactive sample. Radioactive, makes sense, to decay into other nuclear species by emitting particles and energy. Or, pretty much, the time interval required for half of the number of disintegrations per second of a radioactive material to decrease by 1/2. And there are three types of radioactive decay. There is alpha decay, beta decay, and gamma decay. And I will go into all of these types of decays and radioactivity in another video. This video is simply on half-life. So let's do some practice half-life problems. And essentially what half-life is, if you didn't get from my definition, is this is an element. Let's do, what should we do? Let's do uranium-238. This is the entirety of uranium-238. And then it will go down to half of the nucleus is decaying, and then it will go down to 1/4. Kind of like Thanos snapping his fingers. It would go from 1 to 1/2, but that 1/2 wouldn't go to 0. It would go to 1/4, and then 1/4 would go to 1/16, and then 1/32, and 1/64, and so on and so on. And that's something that you need to understand for half-life. And then this is called a parent. This is a parent. It's the original element, but then there's also daughter molecules, and this would be the parent molecule, and the daughter molecule would be the other 1/2, and then this would be the other 3/4. That would be a daughter molecule, but we don't have to worry about that just yet. We will continue on with that discussion in the future. So let's do some practice half-life problems. Problem number 1. The half-life of zinc 71 is 24 minutes. I'm not going to write out the rest of the problem, but if one had 100 grams at the beginning, how many grams would be left after 7.2 minutes have elapsed? So, we have 7.2 minutes divided by 2.4 minutes. And let me just use my calculator here, and that would be equal to 3 half-lives, or 3 cycles of it decaying from half to half to half, aka half-life. And so we have 3 half-lives. And what we need to do is 1/2 to the third power, and that equals, if I'm not mistaken, 0.125. And that's the amount remaining after 3 half-lives. So after these 3 half-lives have passed, that's how much is remaining. So, now we do 100 grams, because we had that at the beginning, times 0.125 grams equals 12.5 grams remaining after 3 half-lives. So this is our answer. Let's move on to another problem. This one will be a little more challenging, and I'll write all of this out. Palladium 100 has a half-life of 3.6 days. If one had 6 0.02 times 10 to the 23rd power atoms. That's a lot of atoms. At the start, how many atoms would be present after 20 days? So if you don't know this already, if you want to try and solve this, pause the video. If you want to just hear the solution, continue watching. After 20 days. So let's attack this. So it has a half-life of 3.6 days, and 20 days have passed. Let's find out how many half-lives that is. 20 divided by 3.6, and that should be 5.56 half-lives have passed. So let's do this times a half. That's how, and this number is what we're solving for again here. And this will just be what we multiply the overall. This is how much we lose each half-life. So after 3 half-lives, we lose this per half-life. Keep that in mind. So now we do 1/2 to the 5.56 power, which equals 0.0213. And I'm doing this all mentally. It's really simple math. And this is a decimal fraction that we have after 5.56 half-lives. So now we do 6.02 times 10 to the 23rd power. And this is going to be in parentheses because you don't want to be confused. Times 0.0213. And now that equals 1.28 times 10 to the 22nd power atoms remain. And that is our answer. This is fun. Let's do a few more of these. And this is just the entire thing for reference. Let's go on. Let's do a more difficult problem this time. This will have to incorporate logarithmic functions, and so if you aren't comfortable with doing those by hand, I don't think anybody is, get out a graphing calculator or just any calculator that has logarithmic functions in it. We're going to be using log 0.5, I believe, for this problem. So first, let me write out the problem. After 24.0 days, 2 milligrams of an original 128.0 milligram sample remain. What is the half-life of the sample? Apologize for my bad handwriting here. So solution. 2.00 mg divided by 128.0 mg should be, let me just check my calculator right here. And that should be 0.015625 mg. I mean, not mg. Yeah, mg. My apologies. And then how many half-lives must have elapsed to get to this amount remaining? This is the amount that is remaining. So we have to do 1/2 to the nth power equals 0.015625. And then we need to do n log 0.5, which should equal log 0.015625, and when n equals log 0.5 over log 0.015625, we divide this. I'm going to use my calculator for this, because this is very hard math. And that should get us to n equals 6, which means 6 half-lives have passed. I hope this clears up some confusion that many people have about half-lives, and this is a very difficult concept for many, and this was just really answering questions on it. I will go into a very, very, very in-depth covering of radioactivity, half-life, alpha decay, beta decay, gamma decay, and all the other parts of radioactivity in a future video. For now, Professor Parth out.